Welcome back, everyone. Houston Math Prep here to talk to you about the alternating series test. Remember, this is our test for conditional convergence. If we have some infinite alternating series, the alternating series test says if you look at the list of terms and you imagine the absolute value of all those terms and look at the limit of that list, so we have a bunch of positive terms. If that list of terms decreases to a limit of 0, then we get that our original alternating series converges conditionally. Remember, this is a weaker type of convergence. We don't actually check for this first. So before we do several examples of our alternating series test, what we want to do is give you the overall outline of what you will do to check for convergence or divergence of an alternating series. So the first thing that we'll do is check for the strongest type of convergence. We'll check for absolute convergence if something converges absolutely. We'll look at the terms, we'll take the absolute value of all those terms, so it'll be a positive list. If that series converges, then we say our alternating series converges absolutely. Remember, that's a stronger type of convergence, so we'll check for that first. And the way we'll check for that once we take this absolute value of all the terms will be to use our knowledge of the test for the positive series, things like the ratio test, the root test, divergence test, integral test, things like that. If something fails to converge absolutely, then the next thing we'll do is check for the weaker type of convergence, which is converging conditionally. Remember, this is weaker, but it is still a way for it to converge. And conditional convergence just means that we can show by rearranging the terms, we can make it add up to anything that we want it to. We'll use the alternating series test to check this conditional convergence, which we're going to go over right now. If it fails to converge absolutely and then it fails to converge conditionally, the only thing that we'll have left to say about it is that, well, it fails to converge both ways, so our alternating series will just simply diverge if it converges neither of those ways. Let's look at several examples here. So we have the infinite sum of -1 to the n over n times root n. So the first thing we'll do is we'll check for absolute convergence. And so we'll look at the sum of imagining all these terms are positive. So that would be the sum of 1 over n times square root n. If I think about what I have on the bottom, I have n to the 1 times n to the 1/2. And properties of exponents tells me that I can add those, and so that would be n to the 1/2, also known as n to the 3/2. I might be able to recognize that this is a p series. So this is a p series, and p is 3/2 here. So if p is 3/2, then we will get that this sum here converges by p series, okay? So if the absolute value version converges, then we get absolute convergence. So this does converge absolutely. So we'll say this converges absolutely. If we want to be a bit more specific than that, then we can say this converges absolutely by p series. Looking at our second one here, I have the infinite sum of -1 to the n plus 1 over the square root of n. So the first thing, let's check for absolute convergence. We'll look at the sum of +1 over the square root of n. Now this is also a p series, but in this case p is 1/2, and when p is not greater than 1, then this will diverge, right? So this right here diverges. But we're not checking divergence in the first step. Remember, all we're checking in this step is, does this converge absolutely? It did not converge absolutely, so we say this fails to converge absolutely. And then we'll move on and we'll check, does it converge conditionally? And the way we check conditional convergence is using the alternating series test. So alternating series test, remember, we look at the limit of what we were just looking at as a sum, and we decide, does it approach 0? Okay, so in this instance, we're saying, does the limit of 1 over square root n equal 0? And we'll notice that square root n gets infinitely large eventually, so this limit is indeed 0, yes. So since that is true, then this series converges conditionally. And when something converges conditionally, it really is always going to converge conditionally by the alternating series test. So you may or may not be required to actually state by the alternating series test, but that's the test used. to show that it converges conditionally. Let's look at this last one here. We have -1 to the n, there's our alternating part, 2n plus 1 over 3n plus 1, the infinite sum there. So first thing we'll check, does this converge absolutely? If we ignore the sign change, then that will simply be the sum of 2n plus 1 over 3n plus 1. And you might notice, for example, using the divergence test, that this limit is actually 2/3. So this would diverge by the divergence test. But really what we're just checking for here is absolute convergence, right? So this fails to converge absolutely. Think about if we're checking conditional convergence though, right? If we check conditional convergence using the alternating series test, what we'll be doing is we'll be looking at the limit of what we were just looking at as a sum and saying, well, is this 0? And no, we just said the limit was 2/3, right? So no, this does not converge conditionally either, right? Because we get a limit of 2/3, the limit is not 0. So this neither converges absolutely, nor does it converge conditionally. So this one diverges. And we could say, I guess, since the last test we used was the alternating series test, then technically that's why it diverges as well. Let's look at two other examples. We have the infinite sum of -1 to the n over ln of n. So if we first check absolute convergence, then we'll be looking at the sum of +1 over ln of n. And we have to figure out how am I going to decide if this converges or not. For this one, I'm just going to use a direct comparison with the sum of 1 over n. And think about why I'm doing that. If I compare just plain ln of n to n, and I say which one has bigger growth, well, this is logarithmic growth, this is polynomial growth. So really, n is going to grow more quickly than ln of n. So this series, because these are reciprocals, we're going to have the opposite direction of inequality. So this sum, the partial sums will be larger than this sum. This is a p series, p equals 1. This is the harmonic series. I know that this diverges. So if this sum diverges, and this one's bigger than this, then this one also diverges as well, right? Now we are not checking for divergence, we're just checking for absolute convergence. So this one simply just, we'll say, fails to converge absolutely. But it has not diverged yet. The second thing we need to check is, does it converge conditionally? So checking conditional convergence, now we look at this as a limit instead. So we look at the limit of 1 over ln of n, and is that equal to 0? Well, ln of n does have infinite growth, so I'd get 1 over something that diverges, and yes, that would be a limit of 0. So since we do get a limit of 0 from our positive list of terms here that we're looking at, then we would say that this one converges conditionally. And I guess we'll additionally say by the alternating series test. Okay, for our last one, we have the sum of -1 to the n plus 1 over the nth root of n. So first checking absolute convergence. Does this converge absolutely? We'll look at the sum of just plain 1 over the nth root of n. Now we want to be careful. This does not have infinite growth. If you look at this, the divergence test will actually work just fine for us, because the limit of this, the limit of the nth root of n is actually 1. So if I look at the limit of the terms, the limit of the terms is 1. So that means the limit is not 0. The divergence test tells us that this series diverges. Remember, we don't jump to diverge right away. That just simply means that this part fails to converge absolutely. So we'll go ahead and we'll look at conditional convergence. So does this converge conditionally? Remember, we'll look at the limit of now 1 over the nth root of n. Is that 0? And we figured out no, this limit already we found was 1. So the answer to this is no, this does not converge conditionally. We don't converge absolutely. We don't converge in this weaker state of conditionally either. So we will diverge here. The alternating series test. Okay, that's several examples of the process of working. First, check your absolute convergence, then check your conditional convergence second. And if it fails to do both of those, then we know that it diverges because it doesn't converge either of the ways that we know for alternating series to converge. Okay, everyone, thanks for watching. Hopefully this helps you. We'll see you in the next video.